So in example 1, a biologist started a bacterial culture with 100 bacteria, and after 4 hours there are 400 bacteria. If the growth is exponential, how many bacteria will there be in 48 hours? So since we're told that we're having exponential growth, it means we are going to select our first model. So our equation is going to have the form, our population P is equal to P naught E raised to the KT. And in each of these, we're given a summary what they are. So P is our amount, or our population at time t. P naught is the starting amount, or the amount at time t equals 0. E is Euler's number. K is the exponential growth rate, and T is time. So note that the units of K and T must match. That is, if the growth rate is in days, then the time must be measured in days. So in our example, we have our bacterial culture starts with 100 bacteria, so that's going to be our P naught. And we're going to put that into our model for step 1. So we have P is equal to 100 E to the KT. So then step 2 in our process is we need to find an ordered pair, so a T and a P that pair up, and use them to solve for K. So our ordered pair is after 4 hours there are 400 bacteria. So we have our T is going to be 4, and our amount is going to be 400 bacteria after those 4 hours. So we can now use this to help us solve for K. So that gives us the equation 400 is equal to 100 E raised to the 4t. So we need to resolve this exponential equation. So from last time, to resolve an exponential equation, the first step is to isolate the exponential. So we divide both sides of our equation by 100, giving 4 is equal to e to the 4t. To undo an exponential with a base of e, we use a logarithm with the same base. So we take the natural logarithm of both sides of our equation, and we have the natural logarithm of 4 is equal to 4t. We divide by 4, we divide by 4, and we get t is the natural logarithm of 4 divided by 4. So let's go ahead and compute this value. So we have the natural logarithm of 4, and we divide that by 4. And that gives us our approximate value that, sorry, I wrote t on all of these. We replaced the t with the 4. This is actually the value of k. So k, and k. So we get k is approximately equal to 0.35. Then step 3 is we put our value of k back into our equation from step 1. And that gives us p equals 100 e to the 0.35 t. So now finally, step 4 in our process is we need to answer our question. So what was it we were asked to find this time? It says if the growth rate is exponential, how many bacteria will there be in 48 hours? So we want P when T is equal to 48. So then we evaluate, we have P equals 100 e to the 0.35 times 48, and that gives us 100. Well, let's just put it in our calculator, actually. So then we would have 100 e to the 0.35 times 48. Let me press enter, and we get the following value. And we're like, yay, we're done. So let's add some commas to see how many bacteria we would have. So we would have 1,977,640,266. All right, so we're super happy, and we go put that answer into Rover, and it tells us we're wrong. So now we need to analyze, well, what went wrong in this process? Well, we actually did nothing wrong in the process. The error occurred right here when we rounded k. To the nearest hundredth. So the question then becomes, since I rounded this to 2 decimal places, how much error do you think that caused in our final computation? Well, we can actually bypass that entire rounding issue by using our calculator. So if we take the natural logarithm of 4 and we divide it by 4, we get this. That's the number we rounded. But instead of rounding, let's go ahead and press our store button and store that as k into my calculator. So now I can proceed without rounding by using p equals 100 e to the k times 48. Well, for step 3 it'd just be kt, where k is in the calculator, and then step 4 would be p equals 100 e to the 48k. So now we just type that exact thing into our calculator. So 100 times e to the 48k. And we get the following value out of our calculator. So we'll notice this time the answer is significantly different. So adding a few commas for clarity, this time we get 1,677,721,600. So the error that we got by rounding to the nearest hundredth too soon was over 300 million bacteria. So as a percent, that would be 1,977,640,266 divided by our answer minus 1. We got about almost 18% error from the actual answer. So the moral of this story is, when we are dealing with exponentials and logarithmic equations, because of their rapid growth rate and the fact that multiplication enhances error, we can't round. Round only when we are told to, and exactly to what we're told to. If we're not told to round, keep the exact value saved in your calculator. Otherwise, just like what we did on the left side, you'll do the process correctly, but at the end you'll get the wrong answer because of rounding issues. So essentially, Exponentials are super sensitive to rounding, so only round when told to, and only round to exactly what you're told to. All right. So exponential growth has some interesting qualities. And the first thing we want to talk about is the doubling time. So the question is, how long does it take for a population to double? Well, if we start with our model, P equals P naught e to the kt, we want T when P is equal to twice our starting amount. So that would be 2 times P naught. If we substitute that into our original equation, we need to solve 2P naught is equal to P naught e to the kt. So we divide both sides by P naught, and something interesting happens. We get the new equation, 2 is equal to e to the kt. Well, notice this does not depend on P naught. That is, the doubling time for exponential growth doesn't depend on how many things are in your initial population. So the doubling time to go from 10 bacteria to 20 bacteria is the same as the doubling time to go from 1 million bacteria to 2 million bacteria. So it is independent of the starting amount. So we continue to resolve by taking our natural logarithm of both sides. And we have the natural log of 2 is equal to kt. And we divide by k, and we get that the doubling time is given by t equals the natural logarithm of 2 divided by k. If we go back up to the formula sheet that was the first page of this, guess it's not there. I thought I'd typed it out here, but apparently that's not a thing. All right, so we have our formula for doubling time. So the only thing it depends on is the growth rate. So to calculate the doubling time, we will use the formula t equals the natural logarithm of 2 divided by k. All right, so example number 2 asks us about that explicitly. So a fish population has a growth rate of 2% per year. How long will it take for the population to double? So we identify our growth rate, K, is 2%. Writing our percent as a decimal, we get 0.02. So then our formula for the doubling time is t equals the natural logarithm of 2 divided by k. Well, that's the natural logarithm of 2 divided by 0.02. When we feed that to our calculator, we have the natural logarithm of 2 divided by 0.02, and we get 34.65. So it's going to take about 35 years. So a couple of things about this. This is assuming pure exponential growth, which would mean that no fish were removed from the population. And in real life, that's not a very good model. We're going to talk about an improved model called logistic growth a little bit later. So this type of doubling when we have pure exponential growth, works better over short time periods with certain things like bacteria and other things where they essentially, for all intents and purposes, have unlimited resources. All right, the next thing we want to talk about is instead of things growing, they can also get smaller, which is what we are going to refer to as exponential decay. So in example 3, we have that carbon-14 has a half-life of 5,730 years, and a bone has 62% of its carbon-14 left. How old is the bone? So the model we're going to want to use this time is exponential decay. You'll notice the only difference between exponential growth and exponential decay is a minus sign on the growth rate. When we have exponential decay, our growth rate will have a minus sign in front of it. So instead of p equals p naught e to the kt, we will have p equals p naught e to the negative kt. All of our constants represent the same thing. The only difference is in the wording. Instead of k being the exponential growth rate, k is going to be the exponential decay rate. One other quirk that pops up quite a bit when we're doing radioactive decay problems is we will be given relative amounts instead of actual amounts. So in our first example, we were told that there was 100 bacteria. In this one, we're not actually given a mass of radioactive carbon-14. We're only told that a bone has lost 62% of its carbon-14. So if an amount is not given, but percents are given, we assume the starting amount is 100%. So if we're not told how much we start with, we just assume that it's going to be 100%. The good news is 100% as a decimal is just 1. So then our step 1 is we use our decay equation. We would have p equals p naught, which in this case is 1, times e to the negative kt, which then simplifies to just p equals e to the negative kt. So now step 2 is we need to find an ordered pair that goes together and use it to solve for k. Well, that's where this comes in. Similar to what we just did with the growth rate, we were able to solve for the doubling time by knowing that what we wanted is we wanted the time when p equals 2 times p naught. Well, in this case, we're given a slightly different set of information. We're given the time when we're going to have exactly half as much as what we started with. So our ordered pair is going to be t and p. It's going to be our half-life. And since we weren't given amounts, half of what we started with is going to be 50%. So if I started with 100%, half of 100% is 50%. So this gives me our ordered pair as 5,730, 0.5. We put this into our equation, and we would have 0.5 is equal to e to the negative k times 5,730. So then, to solve for our exponential, which is already isolated, we use the natural logarithm. The e and the ln undo each other. So we have the natural logarithm of 0.5 is equal to negative 5,730 times k. And we divide by negative 5,730. And we divide by negative 5,730. And this gives us our value of k. So we feed that to our calculator. And we have the natural logarithm of 0.5 divided by negative 5,730. And we get the following number. So a couple of things we have to be careful with, and this is not uncommon when we're working with radioactive decay problems. If we're asked for the decay rate, we need to be a little bit careful. Because on our calculator, it gives us a decimal, but then it gives us this e to the negative 4 stuff. That e to the negative 4 tells us that the number is in scientific notation. And the e to the negative 4 is the same as times 10 to the negative 4th power. Or in other words, I need to move my decimal 4 places to the left. So this number is actually 0.0001296 ... So if we're asked for the decay rate, you can't just say 1.2, that would be incorrect. We would have to move our decimal the correct number of places to the left. If we're just doing this in our calculator, we don't have to bother because we can just go store and save that thing in our calculator as k. So now I've stored my growth rate into my calculator for later use. And that gives me what I need for step 3. So step 3 is I have P equals e to the negative kt, and my k is in my calculator. So once again, we don't want to round or use some rounded value of k. It will cause problems. Step 4 is now we want to answer our question. Well, we were asked, how old is the bone if it has 62% of its carbon-14 left? So we want T when P equals 62%, but we can't use a percent. We have to change it to a decimal. So we put that into our model, and we have 0.62 is equal to e to the negative kt, and we want to solve for t. So we take our natural logarithm once again. E and our ln reduce out. So we have the natural log of 0.62 is equal to negative kt. And we divide by negative k. We divide by negative k. And we get t equals the negative of the natural log of 0.62 divided by k. So we grab our calculator and we go the negative of the natural log of 0.62 and we divide that by k. When we do so, we get the following value out. So we get that T would be about 3,950 years, or round to the appropriate thing. So the bone give or take, is about 4,000 years old. If it's lost 62, if it has 62% of its carbon-14 left. All right, so just to clarify, we can do something very similar with half-life. So the decay rate can be found as follows. So we know we're going to have the point half-life and 50% P naught, or 1/2 of P naught, is going to be this. So if we let H be the half-life, we would have 1/2 P naught is equal to P naught e to the negative k times h. Solving this equation for k, we would once again divide both sides by P naught, and the same thing that happened with our exponential growth is occurring here, that it doesn't matter about the original amount. So we have 1/2 is equal to e to the negative kh. We take our logarithm of both sides once again, the e and the ln reduce out, and we have the natural logarithm of 1/2 is equal to negative kh. We divide by negative h, and we divide by negative h, and this gives us that our decay rate k is equal to the negative natural logarithm of 1/2 divided by h. We can simplify this further by using the quotient rule for logarithms. So by the quotient rule, that's the natural logarithm of 1 minus the natural logarithm of 2 all over h, and we have a minus sign out in front. The natural logarithm of 1 is equal to 0, so then that gives us a minus minus. So finally, minus minus ln 2 gives us positive ln of 2 over h. So the decay rate of an element with half-life h is k equals the natural logarithm of 2 divided by h. So the reason this is helpful, up here we solved for this. We could have skipped all that because we knew the half-life. So in radioactive decay problems, we can get the half-life for free by taking the natural logarithm of 2 and dividing it by the half-life, which was 5,730. And notice we get the same value. You don't have to do this, but it will save you a little bit of time if you do. So there is a formula for us to calculate the half-life. All right. Our next example involves Newton's law of cooling. So it reads as follows. A cup of coffee with a temperature of 160 degrees is left in a room with a temperature of 70 degrees. After 10 minutes, the coffee is 150 degrees. How long will it take to cool to 100 degrees? So this time, we're going to be using Newton's law of heating / cooling. In this case, our coffee is getting colder, not hotter, so we'll be using a cooling law. And in this one, we have to pay attention to our subscripts. So it says a coffee with a temperature of 160 degrees is left in a room with a temperature of 70 degrees. So T is the temperature. T naught is the temperature of the surroundings. So that's our room temperature. So our T naught is going to be 70 degrees. T1 is the temperature of the object at time t equals 0. So this is our starting temp. So our coffee started with a temperature of 160 degrees. So putting all of that into our equation, we get T equals, our T naught is 70 degrees, plus T1 minus T naught, so 160, take away 70, times e to the negative kt. We collect our like terms and simplify a bit, and we get 70 plus 90 e to the negative kt. So that's our model that we're going to use to resolve this problem. So step 2 is we need an ordered pair. So we need a time and we need a temperature. So we're told after 10 minutes the coffee is 150 degrees. So we have 10 and 150. We'll use these amounts to solve for k. So 150 is equal to 70 plus 90 e to the negative 10k. So we need to resolve this equation. So our first step is we need to isolate our exponential. So we minus 70, we'll minus 70, and this gives us 80 is equal to 90 e to the negative 10k. We divide by 90 to continue isolating our exponential. So that gives us 8/9 is equal to e to the negative 10k. We take our natural logarithm of both sides once again, and our e and our ln, being inverses, reduce out. And we have the natural logarithm of 8/9 is equal to negative 10k. We then divide by negative 10 and divide by negative 10, and this gives us k equals the negative natural logarithm of 8/9 divided by 10. So at this point, let's feed that to our calculator. So the negative of the natural logarithm of 8/9 all divided by 10. And then I am going to store that value in my calculator as k. So now, step 3 is I just put k back in, but since it's in my calculator, we've pretty much done that already. So our model is going to look like our equation from step 1, but we've now solved for k. So our model from step 1 is 70 plus 90 e to the negative kt. And once again, k is in our calculator. So then finally, step 4 is we're asked to answer the question. And our question is, how long will it take to cool to 100 degrees? So we want little t when capital T equals 100. So that gives us the equation 100 equals 70 plus 90 e to the negative kt. So we start by isolating our exponential. So to do so, we minus 70 from both sides, giving us 30. equals 90 e to the negative kt. We divide by 90, we divide by 90, and we get 1/3 is equal to e to the negative kt. Using our natural logarithm once again to undo our exponential base e gives us the natural logarithm of 1/3 is equal to negative kt. And we divide by negative k, and we divide by negative k. So finally, that gives us t is equal to the negative natural logarithm of 1/3 all divided by k, and k is stored in our calculator. So negative of the natural logarithm of 1/3 divided by k. Press enter, and we get 93 . So according to Newton's law of cooling, it will take about 93 minutes. All right. Last example before we start our activity. A biologist started a bacterial culture with 100 bacteria. After 4 hours, there are 400 bacteria. The petri dish has a carrying capacity of 1 million bacteria. If the growth is logistic, how many bacteria will there be in 48 hours? So this is a variation of example number 1, whereas example number 1 assumed that the bacteria could grow forever. In this one, the bacteria's population is limited to 1 million because of the medium where they're being grown inside of a petri dish. So we go back to our last model up here, which is logistic growth. And our logistic growth model has a few more things in it than our other models. So our model for logistic growth is f of t is equal to c divided by 1 plus a times e to the negative bt, where our starting amount, so P0, is equal to C divided by 1 over A. We get this, or 1 plus A, by putting T equals 0 in. E to the 0 is 1, and 1 times A is A, so we would get C over 1 plus A. That's our starting amount. So solving this for A, we get that A is equal to C divided by P naught, minus 1, where C is the carrying capacity or the limiting value, and B is a constant determined by the growth rate. So we have to do a little bit more work when we are resolving this. So we identify our C value first off. So C is our carrying capacity. So that is going to be 1 million in this case. And then we have our starting amount is 100 bacteria, which is P naught, but we don't have a P naught in our formula, we have an A. So to calculate the A, which we need, A is equal to C, which is our carrying capacity, so 1,000,000, divided by our starting amount, which is P naught, which is 100, take away 1. So 1,000,000 divided by 100 is going to leave us with a 1 with 4 zeros, so that's 10,000, take away 1, so we get 9,999 for our value of A. So A equals 9,999, and we finally get for our step 1 then that f of t is equal to 1,000,000 divided by 1 plus our A, which is 9,999 times e to the negative bt. So we still need to determine our value of b, but that's going to be our step 2. So now we need an ordered pair that goes together. We know after 4 hours that there are going to be 400 bacteria. So time and our population is going to be after 4 hours, there are 400 bacteria, and we're going to solve for B. So this gives us 400 is equal to 1,000,000 divided by 1 plus 9,999 e to the negative bt, so negative 4b. So then to resolve this equation, we're going to multiply both sides by 1 plus 9,999 e to the negative 4b to get rid of our fractions. So on the right-hand side, they reduce out, and that leaves us with 400 times 1 plus 9,999 e to the negative 4b is equal to 1,000,000. And we need to solve for b. So first thing we're going to do is divide by 400. So 1,000,000 divided by 400 gives us 2,500. So we have 1 plus 9,999 e to the negative 4b is equal to 2,500. Then minus 1 and minus 1 gives us 9,999 e to the negative 4b is equal to 2,499. So then we divide by 9,999, and we get e to the negative 4b is equal to that. Let's see if it reduces. 2,499 over 9,999. And we get 833 over 3,333. So then to undo our exponential base e, we use our natural logarithm. The e and the ln reduce out, and we have negative 4b is equal to the natural logarithm of 833 over 3,333. We divide by negative 4, and we divide by negative 4. So finally, we get b equals to the negative of the natural logarithm of 833 over 3,333 all over 4. So once again, let's put this in our calculator. So we have the negative of the natural logarithm of 833 over 3,333 over 4. And we get this value. And I'm going to store that thing in my calculator as b. Well, that completes step 2, solving for our growth rate. So then our model becomes, for step 3, the model we had up here in 1, so exactly this guy, but now we have b in our calculator. So then finally, step 4 wants us to answer our question. And our question says, how many bacteria will there be in 48 hours? So we want f of t when t equals 48. So we're just going to put that into our equation. So we're going to have 1 million divided by 1 plus 9,999 times e raised to the negative b times 48. And when we do so, we get the following amount. Out of our calculator. So 999,407, because you can't have a fractional bacteria. So notice in this case, we only got 999,406, whereas in example 1, when there was unlimited resources, we ended up with 1,677,000,000 and some change. So logistic growth takes into account that each ecosystem has a finite carrying capacity for whatever you're talking about, whether that be, bunnies in the forest or bacteria in a petri dish. This model is fairly accurate as long as you can measure the carrying capacity actually accurately. All right.